Okay, everyone, we're going to continue with our stoichiometry module, and we are going to talk about how I can use those coefficients in those balanced chemical reactions in order to figure out mathematically various quantities of either reactants or products that will be either used or produced in a balanced chemical equation. So let's start sharing. Okay. Let me get rid of me. Okay, so we were just talking about how the coefficients in a chemical reaction specify the relative amounts in moles of each of the substances. There were two ways that I could read this equation. I could either be microscopic or submicroscopic in that molecular realm. And I can read this equation as two molecules of hydrogen react with one molecule of oxygen to form two molecules of H2O. Or I can look in the macroscopic world and I can have mole ratios. So 2 moles of H2 react with 1 mole of O2 to form 2 moles of H2O. That gives me this guy down here, which is a set of mole ratios. These are the ratios of the moles of the reactants and the products in the chemical equation. So for example, I have 2 moles of hydrogen are required to react with 1 mole of oxygen in order to form 2 moles of H2O. So my ratio is 2 to 1 to 2. Same slide. So let's look at a recipe. What if I thought about making pizza? The number of pizzas I can make depends on the amount of the ingredients you use. Let's say I have a pizza recipe that says for every 1 crust, I need 5 ounces of tomato sauce and 2 cups of cheese. And then I get 1 pizza. So I can express this as ratios: 1 crust to 5 ounces of sauce to 2 cups of cheese to 1 pizza. So these ratios basically are equivalence statements that I can set up conversion factors with. So what if the problem was, how many pizzas can I make if I have 10 cups of cheese using this recipe? Well, here's my equivalence statement. So this is what I'm given, and this is my conversion factor. So for 10 cups of cheese, I can make 1 pizza for every 2 cups of cheese. The cups of cheese is going to cancel, and the answer is 5 pizzas. This is what I will do in a chemical reaction as well. We're going to use the ratio from the balanced chemical equation in the same way that we use the ratio from the pizza recipes. The ratio is going to act as a conversion factor between the amount in moles of the reactants and the products. So here's my equivalency statement. 2 moles of hydrogen for every 2 moles of water. 1 mole of oxygen for every 2 moles of water. 1 or 2 moles of hydrogen are necessary to react with every 1 mole of oxygen. These ratios are going to act as conversion factors between the amount in moles of any reactant and the amount in moles of any product. This particular ratio is looking at the moles of the reactant H2 and the moles of the product H2O. So I'm looking at the relationship between those two substances. But I can use any of the coefficients in this way, and I can relate amounts of any reactant to any other reactant, any product to any other product, or any reactant to any other product. So here's a problem. Suppose we react 2 moles of H2. How many moles of H2O are going to form? So this is my given. I have 2 moles. This is my conversion factor, which is based off this equivalency, which is based off the ratio of the coefficients of the balanced chemical equation. Moles of hydrogen cancel. I'm left with moles of water, which is what I want. What I end up is 2 moles of water is my answer. This is stoichiometry. So I can extend that and calculate the mass of a product from the mass of a reactant. I need to do this calculation, the mole ratio from the balanced chemical equation. If my reaction is not balanced, this does not work. I also need the molar mass of the reactant and the molar mass of the product. We know how to go from moles to grams and from grams to moles using the molar mass. So now I can just tag that on to the end of my mole ratio from my balanced chemical equation, and I can relate these moles to masses that I can weigh and measure in the lab. So stoichiometry is basically chemical arithmetic. It's going to allow me to convert from the grams of a substance that I want to use in a reaction, and then calculate the grams of the other reactant that I need to use in the reaction. For example, here's a reactant. These two are reactants. The ratio is A moles of A is equal to B moles of B. If I have grams of A, I want to react this many grams of A. I can convert that into moles of A using the molar mass of A. Well, this is going to be the mole ratio. If I have moles of A, I can use the coefficients from the balanced chemical equation to figure out how many moles of B that I need to react with that amount of A that I plan on using. And then using the molar mass of B, this allows me to calculate the grams of B that I need to use in this reaction. So by doing this, let's say I have a specific amount of A that I want to use in my chemical reaction. I can also calculate based on that amount of A how much B I need to use in this reaction. Remember, these chemical reactions are occurring on that microscopic level, so that molecules of A are reacting with molecules of B. Using the same method, I can calculate the amount of C and D that I could produce if I used a given amount of A. So this is a very powerful in chemistry. I can't just throw things together in a lab and hope for the best. I need to calculate all of the amounts of the two reactants to get an effective reaction. And then I can calculate based on these mole ratios the amount of products that I can expect as well. So here's an example. How many grams of sodium hydroxide are needed to react if I know I have 25 grams of chlorine? So I know I have 25 grams of chlorine. I want to know how many grams of the sodium hydroxide I need. to fully react with that chlorine. So what I'm going to do is I'm going to take the grams of chlorine. I'm going to use the molar mass of Cl2 that I get off the periodic table. I'm going to calculate the moles of Cl2. This is a 2-to-1 mole ratio between sodium hydroxide and chlorine. So I'm going to use that to convert between the moles of chlorine to the moles of sodium hydroxide that I need in order to react with that amount of chlorine. Using the molar mass of NaOH, I now can calculate the grams of sodium hydroxide that will react with 25 grams of chlorine. So now I have control. I know I want to use 25 grams of chlorine. I have to figure out how many grams of sodium hydroxide that will react with that, and then I can do the reaction in the lab. So this is the setup, and I'm going to use conversion factors so I can track what cancels and I can track what doesn't. So this is my given, 25 grams of chlorine. If I stopped right here, I have moles of Cl2 in 25 grams. But I don't want that. I want to figure out how many moles of NaOH that will react with the Cl2. And then my final conversion is how many grams in that molar amount. So this is the molar mass of Cl2. This is my mole ratio from the balanced chemical equation. And this is the molar mass of NaOH that I calculate using the periodic table. So this calculation tells me that in order to react with 25 grams of chlorine, I need to add 28.2 grams of sodium hydroxide into my reaction mixture. 28.2 grams is going to be the stoichiometric amount necessary to react with 25 grams of Cl2. So let's practice. How much carbon dioxide in grams would be formed if I use 10 grams of C5H12? And I have excess oxygen. I can assume excess of the other reactant if I'm only given one amount of one reactant. So again, I'm going to go from grams of A to moles of A to moles of B to grams of B. This is using the molar mass of A. This is using the mole ratio between A and B. This is using the molar mass of B. So I have 10.0 grams of C5H12. So what I need is to calculate the molar mass. How many grams, that goes on the bottom because I want to cancel, of C5H12 do I need, or do I have in 1 mole of C5H12? So that's the molar mass. I'm going to go ahead and take my calculator. I'm going to say 12. Nope, sorry. I'm going to say 5 times 12.011. That's equal to 60.055 plus, I'm going to say 12 times 1.008. This molar mass of the C5H12 is 72.151 grams per mole. Now, what is the ratio between the moles of C5H12 and the moles of CO2? I use the coefficients of the balanced chemical equation So for every 1 mole of C5H12, I make 5 moles of CO2. I don't want moles, I want grams. So I'm going to use the molar mass of CO2. For every 1 mole CO2, I have 44.02 grams of CO2. When I look at this, grams of the C5H12 cancel with grams, moles of C5H12 cancel with moles, moles of CO2 cancel with moles of CO2. I'm left with grams of CO2 as my units, which is what I want. So in my calculator, I'm going to go 10 times 5 times 44.02. And then I'm going to divide that by 72.151. And what I'm going to get is 30.5 grams of CO2 is going to be prepared if I react 10 grams of C5H12 in this reaction. So this is stoichiometry. It's useful when I go from grams to moles to moles to grams because those are quantities I can measure. When you show your work, I want you to show grams of what substance. Grams of C5H12 can only cancel with grams of C5H12. Grams of C5H12 can't cancel with grams of CO2. So in this section, you need to not only put the unit, is it grams or moles, but you also have to put what substance you're talking about, because otherwise you're going to get very confused and you're not going to know where you are in your calculation. You always want to follow the units. Here's another example. How many grams of hydrogen gas are needed to produce 85.2 grams of ammonia, given the following unbalanced chemical equation? Well, I need to balance this because otherwise I don't know what the appropriate mole ratios are. So let's do that. Here's a trick. This is even, this is even, this 3 is odd. Well, I can't have fractions. So the first thing I'm going to do is put a 2 here. So that gives me 2 nitrogens and 6 hydrogens. Well, I have 2 nitrogens, so that's balanced. How can I get 6 hydrogens here? Well, I just have to put that coefficient. This gives me 6 hydrogens and 2 nitrogens. This gives me 6 hydrogens and 2 nitrogens. That's equal, so this is now balanced. So let's start the stoich calculation. I have 85.2 grams of hydrogen gas, which is H2. Remember, this is a diatomic molecular element. So is nitrogen. You have to take that into account because the molar mass of hydrogen is 2 times the mass of hydrogen atom. So for every 1 mole of H2, I have 2 times 1.008. So that gives me 2.016 grams of H2. I want to convert from moles of H2 to moles of ammonia. So I'm looking at the ratio between that. For every 3 moles of H2, I make 2 moles of ammonia. Remember, this is the mole ratio from my balanced chemical reaction. And then I can convert to grams. For every 1 mole of NH3, I have 14 plus 3 times 1.008. That gives me 17.02 grams of NH3. When I do this, remember, this converts to moles of H2O using the molar mass. This is going to go from moles of H2 to moles of NH3, and this is going to go from moles of NH3 to grams of NH3, also using the molar mass. So when I look at this, what I'm going to do is 85.2 times 2 times 17.02, enter. That gives me 2,900 and something, divided by 2.016, enter, divided by 3, enter. So this gives me, if I use that much hydrogen, I'm going to get 480 grams of NH3. Now let me make sure I did this correctly. So I have 85.2 times 2 times 17.02 divided by 2.016 divided by 3. Yeah, that's the right answer. I want to make this 0 significant when I round. So that's why I'm going to put that dot there. And this would be the answer. Here's another that we can try. The first thing I want to look at, right? I have 92.0 grams of aluminum. This is the product. I want to see how many grams of that reacted if I use 92.0 grams of aluminum. Well, I have a problem here because it's not balanced. I have 3 nitrates there and only 2. Because this is even and this is odd, I'm going to put a 2 here. That'll give me 2 times 6. I need 3 here to give me 6 nitrates. So that means I'll have 2 aluminum and I'll have 3 magnesiums. So here I have 2 aluminum, 6 nitrates, and 3 magnesiums. And then I have 2 aluminum, 3 times 2 is 6 nitrates, and then 3 magnesium. That is equal, so I am balanced. So if I start out with 92.0 grams of aluminum, I'm going to convert to grams to moles of aluminum. So for every 1 mole of aluminum, I'm going to look on my periodic table, and I'm going to see that for every 1 mole of aluminum, I have 26.982 grams of aluminum. That's the molar mass of aluminum. I'm going to use the mole ratio to go from moles of aluminum to moles of aluminum nitrates. So for every 2 moles of aluminum, I need to react 2 moles of aluminum nitrate. I'm not going to reduce this here when I set up my work. I know that 2 over 2 is 1, but I never reduce my coefficients. I'm just going to take that into account at the end. And then I'm going to need to go to, this is moles. So for every 1 mole of Al, NO3 I need to calculate the grams of AlNO3 So in 1 mole of aluminum nitrate, I have 26.982 plus 3 times 14, that gives me the amount of nitrogen, plus 9 times 16, because I have 3 times 3, 9 oxygen atoms in that 1 mole. That gives me a molar mass of 212.98 grams. So let's do this. Grams of aluminum cancel with grams of aluminum. Moles of aluminum cancel with moles of aluminum. Moles of aluminum nitrate cancel with moles of aluminum nitrate. Now I don't actually have to put this 2/2 in my calculator. So I can just take 92 times 212.98, enter, and then divide this by 26.98. And what I'm going to get is 726 grams of aluminum nitrate is made every time 92 grams of aluminum is produced. Here's a little bit more complicated problem. I have aluminum foil, so I have a square, which is 1 centimeter, but then I have a thickness because it's a foil. So this is like a 3-dimensional object. That thickness is 0.450 millimeters. I want to know how many grams of bromine were consumed and how many grams of aluminum bromide were produced. Now, what is the reaction? That's the first thing we have to figure out. We have to produce a balanced chemical reaction for this. So what I'm going to do is I'm going to say aluminum plus, which is a solid metal, plus Br2, which is a liquid, goes to, what is the formula for aluminum bromide? Aluminum is a +3 ion, bromide is a -1 ion. So my formula is AlBr3, all ionic solids are solids. You need to know that aluminum is referring to aluminum metal, that bromine is a diatomic molecular element. So when I react with bromine, I'm reacting with Br2. And then if I'm forming aluminum bromide, that the formula for AlBr3 is going to be, or the formula for aluminum bromide is going to be AlBr3 based on our nomenclature rules. So that's why you have to constantly think about nomenclature. So I'm going to start, because this is odd and this is even, I'm going to put a 2 there. That gives me 2 aluminums. 2 times 3 is 6 bromine. To get 6 bromine, I'm going to use a 3 there. So my balanced chemical equation is this. All right. Now, remember density relates mass to volume. Well, I have an aluminum foil. I need to know the mass of that aluminum in order to do the stoichiometry problem. So my volume of the foil is going to be length times width times height, which is going to be 1.0 centimeter times 1.0 centimeter. Now notice this is in millimeters. So 0.540 millimeter. I know that I have 10 millimeters for every 1 centimeter. And what I'm going to get is 0.054 centimeters. So this is this one, 0.054 centimeters. Notice the volume of the foil is then 1 times 1 times 0.054. So it's 0.054 centimeters cubed. So this is the volume of the aluminum. Now, if I have 0.0054 centimeters cubed, I can use density as a conversion factor. For every 1 centimeter cubed, I have 2.70 grams of aluminum, right? The centimeters cubed will cancel, that gives me grams. So I have 0.054 times 2.70, and I get 0.1458 grams of aluminum. This is the amount of aluminum that reacted. So I have 0.1458 grams of aluminum. What I want to know now is how much bromine did that react with? So for A, I have 0.1458 grams of aluminum. I'm going to convert that to moles with the molar mass of aluminum. For every 1 mole of aluminum, I have 26.982 grams of aluminum off the periodic table. I'm going to use the mole ratios between aluminum and bromine. For every 2 moles of aluminum, I need 3 moles of bromine. And then I'm going to look at the molar mass. For every 1 mole of Br2, how many grams of Br2 do I have? Well, I have 79.904 times 2. And that gives me 159.808 grams. Oops. Why did I put that there? That's the molar mass. So that gives me 159.808 grams of Br2 as the molar mass. So I'm just going to check my units. Grams of aluminum cancel with grams of aluminum. Moles of aluminum cancel with moles of aluminum. Moles of bromine cancel with moles of bromine. I'm left with grams of bromine. So I am good. And what I am going to do is now plug this into my calculator to figure out the answer. So I have 0.1458 times 3 times 159.808, so that's across the top, divided by 26.982, enter, and then I'm going to do divided by 2. That's going to give me to 3 sig figs, 1.30. That's the amount of bromine that is going to react with that amount of aluminum. I also want to know how many grams of aluminum bromide were produced. So for B, I could either use the amount of bromine that I just calculated, or I'll just stick with the amount of aluminum that I just calculated. So I'm going to do 0.1458 grams of aluminum. I already know that 1 mole of aluminum is 26.982 grams of aluminum. Here now, I am looking between aluminum and the product. So that's a different mole ratio. That's 2 and 2. So for every 2 moles of aluminum, I make 2 moles of AlBr3. Now I just need to convert to the grams of AlBr3. For every 1 mole of AlBr3, I have how many grams of AlBr3? So what I'm going to have is aluminum, which is 26.982 plus 3 times the mass of bromine, which is 79.904, and that gives me 266.69. So let's check. Grams of aluminum cancel, moles of aluminum cancel, moles of AlBr3 cancels with moles of AlBr3. Now I should be able to calculate this. Remember, I haven't reduced that. I'm just going to discount that. So I have 0.145 times 266.69, enter, divided by 26.982, and I'm going to get 1.43 grams of AlBr3 produced. So A and B were answered using the same information, but it all hinged upon using the idea that I had a piece of foil. And in order to figure out the amount of aluminum, I had to use what we did in chapter 1, which is using the density equation. So this is a perfect illustration of how chemistry is cumulative. Chemistry never ends. What we learn in chapter 1, we use all the way forever, depending on how far you go in chemistry. But this is how you do stoichiometry. And the next time we come back to talk, I'm going to talk about limiting reagents and also percent yield. So that's all for now. Bye.